The last transformations that we're going to work with are the vertical and horizontal stretches and compressions, also known as stretches and shrinks. Let's look at the formal definitions of each, and then again we'll talk about more of a working definition. How do we decide what we're going to do and how it's going to affect the graph? So when the right side of a function y equals f of x is multiplied by a positive number a, the graph of the new function y equals a times f of x is obtained by multiplying each y coordinate on the graph of y equals f of x by a. The new graph is a vertically compressed if a is between 0 and 1, or a vertically stretched if a is greater than 1 version of the graph y equals f of x. So again, I know this is a lot of information, but let's kind of pick out what's important. Well, it's important to recognize that the graph is going to be compressed if our a value is between 0 and 1, and it's going to be stretched if a is greater than 1. So that's going to help us with a visual idea of what the graph's going to look like. So if we're multiplying the entire function, so again, it's outside that set of grouping, then it's going to be compressed. If it's between 0 and 1, it's going to be stretched if it's greater than 1. The other piece we want to take away is that to determine how much it is compressed or stretched, we're going to multiply the y coordinate of each point by a, whatever a may be. And that's going to help us to find new points on the graph that has either been compressed or stretched based on this value of a. For horizontal stretches and compressions, if the argument x of a function y equals f of x is multiplied by a positive number a, the graph of the new function y equals f of a times x is obtained by multiplying each x coordinate of y equals f of x by 1 over a. So a horizontal compression results if a is greater than 1, and a horizontal stretch occurs if a is between 0 and 1. So what I want us to notice here again is that horizontal stretches and compressions occur when the argument is multiplied by some number a. And I want us to notice that because we're multiplying by 1 over a and not by a, it actually is going to do the opposite of what we would expect to make sense. So up here in vertical stretches and compressions, if our number is between 0 and 1, then it makes sense that it would compress it. And if it's greater than 1, that makes sense that it would stretch it. But with horizontal stretches and compressions, it's the exact opposite. So if a is greater than 1, that's actually going to result in a compression. And if it is between 0 and 1, that's going to result in a stretch. The other piece that we want to take away is that when we're working with horizontal stretches and compressions, we want to multiply our x coordinate, and it's by 1 over a, not by a. So let's look at our example here. Use the graph of y equals f of x below to sketch the graph of g if g of x equals f of 2x. So what are we being asked here? Well, here's the graph of f. Now we want to sketch the graph of g over here on the side. And g is going to be f of x, except that we have multiplied the argument by 2. So remember, if we multiply the argument, that's going to be a horizontal stretch or compression. And since we are multiplying that argument by 2, we know that it's going to be a horizontal compression. So our graph is going to kind of look like it was squished in horizontally. And we're going to do that by multiplying our x-coordinate by 1 over a. So remember, a in this case is 2. 1 over a would be 1/2. So what I'm going to do is take all of my points here on this graph, and I'm going to divide their x-coordinate by 2, or multiply by 1/2. So let's start with -8, 1. And we are going to multiply the -8 by 1/2, which is going to result in -4. The y value, or the y coordinate of this point, is going to remain the same. So we're going to end up with a point at -4, 0. So there's our first point. Let's get that a little bit closer to the line here. Third time's a charm, that's what they say, right? Well, it's still a little bit low, so let's see if we can edit it here and move it up a little bit. They say third time's a charm, but they lie. All right, so now we've got our point where we want it. So now let's look at our next point on our graph. We have -2, -6. So again, we're going to take our x value of -2. We're going to multiply it by 1/2, or divide by 2, and that's going to give us a point of -1, -6. So we come over here to -1, -6, and we put our point. And again, my stylus doesn't seem to want to be cooperating with me, so I'm going to shift it over a little bit here. And we're going to continue this process until we get all of the points that were on this original graph replotted. So 0, 0, well, dividing 0 by 2 doesn't do anything, so 0, 0 is just going to remain at 0, 0. 2, 6, 2 divided by 2 is going to end up being 1, 6. So we've got a point at 1, 6, and then 8, 0 is going to end up being 4, 0. All right, so now we are ready to connect our points on our graph, and we're going to end up with a horizontal compression. Now, it is worth mentioning that the scale on these two coordinate systems are different, so it may not look as obviously compressed as what it would have if we had been using the same scale. But this would be the graph as it appears on the new coordinate system. So you can see that here each of these is about half as big as the blocks over here. So again, but you can still see a little bit of compression occurring even though the blocks here are twice as big as the others. So keys here is to remember that vertical stretches and compressions occur when we multiply the entire function by a number, and it makes sense. So a number larger than 1 stretches, a number between 0 and 1 compresses. Horizontal stretches and compressions occur when we multiply just the argument by a, and it's opposite of what makes sense because we're actually dividing by a, or multiplying by 1 over a. So if a is greater than 1, it ends up in a compression, whereas if a is between 0 and 1, it ends up in a stretch.